Okay.
Thank you, Savka, for invitation for me to present at your webinar. My name is Dmitry, and I'm a seismologist and originally from Russia. And Savka and we got a PhD in the same organization in the Institute of Physics of the Earth in Moscow. Is it correct, Savka?
Yes.
Yeah. So I worked in Russia, and then I joined company. Now it's called Institute of Mine Seismology, which is specialized on seismic monitoring in mines. I expect that not all participants of this webinar are familiar with the mining context, and I'd like to start showing you a short video of rockburst. So how does it look like? Can you see the video?
Yes, we see the video, but I have problem with the recording. Vikaub, where do I need to do this? I think it is recording. Yes.
It has gone now.
It was recorded.
Yes.
Yeah.
Please continue.
So what is shown here, it's a tunnel. So this is a sidewall back of the tunnel. And as you see people here, so it's a height approximately 5 meter, horizontal dimension also 5 meter. So on the side, we see a so-called ground support. It's you see parts of the rock bolts, mesh, shotcrete, and we will talk about this a little bit later. And this is the face of the tunnel, which is not supported. So this is a rock, and this is a tunnel in a hard rock. So what do you mean? Do I mean by hard rock? So if you take pieces of this rock and you want to break it with your hand, throw it on the floor, it's very difficult to do it because rock is very strong. And looks like everything is quiet, stable. And let's wait a little bit. So suddenly we see that the side wall of the excavation explodes. So this hard rock, it's just suddenly ejected. As you see here, it's ejected from the side wall with quite significant velocity. So there is no blast. It's quite this phenomenon that happens on its own, and this is what in mining we call rockbursts. We'll play again. And as you can imagine, this phenomenon is very dangerous. Luckily, in this case, nothing happened with the people working, but if you can imagine a situation when these people were stayed in different locations, there may be quite bad consequences of this rockburst. So my presentation is focused on these rockbursts and what's the role of seismology in the assessment of hazard likelihood of these rockbursts. So initially we'll go through definitions and terminology. Then we very briefly talk about principles of assessment of rockburst hazard. And then bigger block of presentation, we'll talk about specifics of seismic data recorded on rockburst-prone mine, especially about types of seismic source mechanisms. And finally, we'll discuss utilization of seismic data in assessing rockburst hazard. Again, next slide is just to expecting that the auditorium is maybe not very familiar with the mining. Here I show different mining methods. As you can see, there is in blue, it's shown here the ore body, So it's a part of the rock mass which is valuable from the perspective of extraction. And this ore body have different shapes. It can be very significant, very thick. It can be very narrow horizontal, narrow vertical, or inclined. And usually in mining, valuable piece of rock, they're extracted by blasting. But to implement all of this, it's necessary to establish a network of tunnels. And this network may be very sophisticated. So there are, as you can see here, a lot of tunnels in different directions in a deeper part of the mine. And according to design, these tunnels are expected to be stable. So they must be provide access people or equipment. They sometimes used for ventilation and other purposes. But sometimes this stability is compromised. They may experience static damage, or as we discussed in the beginning, it may be dynamic damage of these tunnels. So rockburst is defined in a Canadian Rockburst Support Handbook as a damage to an excavation that occurs in a sudden and violent manner and associated with a seismic event. So this is the definition which I follow in this presentation. So when we talk about rockburst, we're talking about damage which happened in a sudden or violent manner. It's important to keep in mind that there are varieties of rockburst damage mechanisms. There are, broadly speaking, two groups of them. One is called rockfall due to seismic shaking, where major driving factor of the damage is an incoming seismic wave. So if you can imagine tunnel, if there is a fractured rock around tunnel, supported or unsupported, and if this rock mass experiences strong ground motion, shaking, passing seismic wave, stress wave, and because of inertia of this block, then can sometimes be moved into the excavation, and this can be damaged. But the driving force of this process is an incoming seismic wave. And it's very similar to what is the damaging mechanism in case of tectonic earthquakes, which we'll mention a little bit later. But there is also another important class of the rock-based damage mechanism. It's a rock bulking due to fracturing. Here, a major factor is a stress around excavation. So when you have a concentration of stresses around excavation and rock is hard and brittle, sometimes it's without impact of any external seismic wave. It can initiate process of fracturing. As the rock mass is fracturing, it increases in volume, and there is a preferable direction of rock to move during this process, obviously not into the rock mass, but rather into the excavation. And if this process happens over a fraction of a second, so it's dynamic. So this is the essence of this second type of rock-based damage mechanism. It's also called strain bursting. So rock-burst, it's a like total umbrella of the damage processes. This process, which is shown on the right, it's called strain burst. Another term that we will definition which we'll use today, it's a rock-burst hazard. So it is defined as a probability of occurrence of damage of rock-burst damage of a given severity in an excavation at a given location, a given time period in future. So for practical point, it's important to evaluate if you have a tunnel, and we would like to know, for instance, during the delta T 1 year, next year, what is the probability that this tunnel experience light rock-burst damage or severe collapse during the rock-burst? And it's possible to evaluate this probability, and it's not a purely seismological problem. It's a A lot of components are required for this assessment. For instance, it's important to know what the rock type. Is it a hard rock or soft rock? How much stresses are around tunnels? It's also important to know what's the planned mining at the mine, because you may have tunnel, and if this tunnel away from mining and there is no much mining happening near this tunnel, probably rock burst hazard will not change. It may be low, but if you have a planned intensive mining around the tunnel, we expect that maybe bring more stresses close to tunnel. We may activate some geological structure which can deliver large-scale slip type event, and in this case, hazard will be different. So it depends on not only what happened in the past, what is planned in future. Seismic data plays important role in the assessment of hazard, and we'll talk about this in the final part of presentation. And lastly, rock burst hazard depends on ground support. Again, as I expect, many people are not very familiar with the ground support. I very briefly talk about this. So when I talk about ground support, I mean the different, it's called rock boats, which are installed in holes drilled on the perimeter of tunnel, and these pieces of steel are quite often installed and grouted to reinforce rock around the excavation, around the tunnel. Sometimes it's only deeper part, anchor of the boat is grouted, and then this rock boat has a function of holding rock between the anchor point and the plate on the surface of excavation. And also there is another type of ground support. It's a surface support, which different kinds of mesh, shotcrete, and function of this aerial support is to retain. So for instance, keep pieces of rock between the rock bolts, or if one of the reinforcement component is damaged, so it mustn't fall into the excavation, mustn't eject into excavation. So there is a retaining function of ground support. And in terms of the problem of rock burst, it's reasonable to say if you put a lot of reinforcement aerial support elements in the excavation, probably will reduce chances of dynamic damage of the excavation. If you put less support or poor quality ground support, chances of rock burst damage will increase. So just the main point here is ground support plays important role in the likelihood of rock burst damage. During the presentation, you will also see that we operate with different types of hazards. As I mentioned, there is a rock burst hazard when we talk about probability of violent damage of excavation. But we also will talk about seismic hazard and ground motion hazard. How we define it? Seismic hazard, we're talking about probability of occurrence of seismic event in a given space, given period of time in future, given magnitude. Ground motion hazard, we talk about probability of exceedance of strong ground motion at particular location, usually again in a given time period in future. And all of this definition, we talk about probabilities. Why is it important to quantify hazard in terms of probabilities? Because firstly, we can check our assessment. If we give probability for future, then after some period in future, we can test how often seismic event occur in the area where we predicted high hazard, or how often ground motion exceeded predicted level, or how often rock burst happened in the predicted areas of high rock burst hazard. So first utility, we can test the performance of all this assessment. And second objective of using probabilities, then we can deliver results, convert results, probability of exceedance and no rate of exceedance, we can convert it to likelihoods of risk assessment matrix which is used at the mine. So we may have a probability of rock-based damage, but this probability may be so low that it corresponds to the rare likelihood. And in this case, geotechnical engineers of the mine have used this, put more efforts, may put less effort to manage this hazard because associated risk will be lower as compared to situation when the rock-based hazard belongs to the likely category of the risk assessment matrix. Now this slide and next slide I will show you, they look a little bit complicated. So this is what I show you is a computational procedure, how it's possible to evaluate rock-based hazard. And we will not go into details how this procedure works. So my main intention just to show here what's the role of seismic data, seismological method in the assessment of rock-based hazard. And second thing that is just very briefly I'll show the principle of what is the main principle of assessment of rock-based hazard. So as I mentioned before, to assess rock-based hazard, we need to bring various pieces of information from rock mass properties, stress model. We're trying to evaluate what's the depth of failure, depth of fractured rock is expected around tunnel. Then we use, as we talk about later, seismic data in different ways in this assessment. And this second slide, it's all these calculations. They converge into the diagram comparing demand and capacity of ground support system. So maybe it doesn't sound very understandable, very clear for you. So what I'm talking about, it's for each tunnel, we want to compare what the capacity of ground support system and compare what the expected demand on this ground support during the rock burst. And this diagram has two axes. One is the displacement, another energy. And these are not seismological parameters. It's not seismic energy. It's not seismic displacement. So here what we are talking about, so if you have a tunnel with installed ground support on the perimeter of tunnel, so we have this fractured rock, and this fracture may happen dynamically, or it can be motion of this fractured rock due to impinging seismic wave. And here we are talking about displacement on the surface of excavation. This is displacement which loads rock bolts or loads surface support. So this horizontal axis of the diagram, it's a surface displacement. And vertical energy, we are talking about kinetic energy of this block of fractured ground. So here in my presentation, when I talk about displacement and kinetic energy, I'm not talking of displacement, slip displacement along the fault or seismic energy. I will talk about displacement on the surface of excavation and kinetic energy of the block of ground which is supported, which is reinforced. So we have a displacement energy, we have a capacity of ground support. As more and more displacement happens, that less and less energy the ground support can absorb. And another trajectory, it's if dynamic failure happened, so we expect it will have a displacement component in this dynamic loading and energy component. And this is the essence of assessment of rock-based hazard. We want to forecast our demand in terms of energy and displacement and compare with the remnant capacity of ground support. So if our demand is below capacity, it means rock-based hazard is low. if expected demand exceed ground support capacity, then rockburst hazard is high. So this is a very, in a simple way, the main idea of the methodology. So now I'm try to see how seismic data can be used in this assessment. So this block of the diagram, seismic data, what's the role of seismology in this assessment? So let's quickly look at the classical seismology, which deals with the tectonic earthquakes, and which instruments do we have. As Kostrov defined, source of tectonic earthquake, it's a shear fracture of the earth material along a typically a planar surface, which is initiated over a small area and then propagates at a velocity not exceeding the velocity of P waves. So if we are dealing with these seismic sources, then we have a quite big toolbox what we can do with seismic data. So we can measure seismic moment from recorded seismograms, and this can be interpreted in terms of product of shear modulus, slip area, average slip. Or equivalently, we can use such term as seismic potency, which is simply product of slip area and average slip. If we evaluate it from the source spectra corner frequency, we can use it to invert source radius. There are different equations. We can assess displacement at the source, with average slip from seismic potency, seismic moment. We can also, looking at the acceleration waveforms, invert or evaluate near-fault peak ground velocities. And looking at the radiation pattern of seismic signals, we can evaluate what was the orientation of this shear fracture plane surface or fault slip surface, and also what was the direction of slip. Are we talking about strike slip, normal faulting, reverse faulting? So in terms of this classical model of seismic source, we have acquired many instruments which we can use to infer information about what happened in terms of source, in terms of geometries, orientations, and mechanics. And also another aspect of marine seismology, it's quite well known that the major damaging aspect of tectonic earthquakes, for instance, if you're talking about damage to building, is related to strong ground motion. So for instance, this is show results of statistical analysis of causes of earthquake damage to buildings and the major mechanics of damage is shaking. So for instance, landslide or fault rupture, it's a very infrequent causes of damage of the buildings during earthquakes. So typically, hazard associated with tectonic earthquake relates in terms of the intensity of ground motion in the foundation of building. So we have a fault and rupture in the deep part of the crust, seismic waves propagate and they are amplified in the near surface layers. And this strong ground motion, this is a major cause of the damage to the, in case of tectonic earthquake. And this is also quite a lot of tools, a lot of models exist in earthquake engineering to quantify this impact and how to translate it to the probability of damage of the buildings. And now the big question, how is it applicable in mines? And my answer, yes. We definitely observed some of the seismic events in mines. They match this model, which was mentioned before, model of tectonic earthquakes. So we do observe seismic events which have a seismic radiation which correspond to seismic source model of tectonic earthquake, this double couple model. So from seismic data, we can evaluate this mechanism, and we can talk about what's the orientation of potential shear failure surface or slip plane. We can talk about direction of slip. And in this case, we can use all this toolbox, which I mentioned before, about evaluating the dimensions of the source, amplitudes of displacement, velocity of slip, and what will be impact from this event to the nearby excavation. This classical seismology works for this kind of events. And to identify these events, we prefer to calculate seismic source mechanism, and we expect these events obviously should populate this central part of Hudson source type plot or Loon diagram. So we expect them to be somewhere in this area. And this is an example from a real mine. So what is shown in the left, it's a vertical section. Here, vertical section along the mine. So gray, it's a mined out stopes. And this smaller horizontal section, it's a tunnels. And as you see scale, it's a grid size between, it's 100 meters. So these tunnels, approximately 5-6 meters. And in the bottom, we see the corresponding plan view for the same part of tunnel. And what is shown here is seismic events, seismic source mechanism. And we see one cluster of events, which is on the section view is here. And plan view, these events are located away from the excavation in the footwall of the ore body. And interesting aspect of these events, they are, if you plot them on a Hudson source type plot, they will be in the central part of it. And another interesting thing that these events, as you can see in the horizontal section, they tend to be aligned, clustered along the planar surface. So on a plan view, you can see them are distributed, but looking in the direction, horizontal direction, we can see they have a tendency to be distributed along horizontal plane. And if you plot on the stereo that this common location plane, which is shown here in magenta, so it's a deep into the northeast. And then we plot a nodal planes of seismic source mechanisms. We have quite good fit of one family of nodal planes with this common location plane. So this is where classical seismology works, double couple or close to double couple mechanism, and they can be interpreted as episodes of sudden slip along the potential subhorizontal weakness, which was affected by all this mining. So this is an illustration that we do observe classical events with double couple mechanism, and for which we can use all this toolbox developed in crustal seismology for interpretation and analysis and evaluation of impact to the tunnels. Why I show this case? Because actually just next to this cluster, we have another group of events. So now if you look at this area, this group of seismic events, which are now located very close to the tunnels and stopes. And if you plot this seismic source mechanism of these events on Hudson source type plot, they are not anymore in the central part of it. They are more clustered in the bottom right part. So they have quite significant implosive component, so this order of 50%. And also they shifted to the right in the direction of the closing crack model. So we call this like a pancake shape deformation. So it's a quite strong cluster here. And in this case, nodal planes are not really very constrained for this type of mechanism. P-axis of these mechanisms are a bit rotated compared to previous cluster, and they tend to be orthogonal to the direction of the tunnels. As you can see, these are Px is now oriented to the east and a little bit to the south, orthogonal to tunnels. So this is an interesting case. We see this quite a lot of events, but they don't really match this classical model of seismic source double couple mechanism. And it's not really observation only for this mine. So we observed quite many other mines. So here I show this is the same mine and little bit different subset of events. Here I show the tunnels are colored according to maximum stress on the perimeter of tunnel. This just to get impression about what the stress field around this mine. And you see that the upper part and lower parts of tunnels and sidewalls of stopes, they are colored in red. So this indicates, in this case, condition stress is subhorizontal at this mine and approximately orthogonal to the ore body. So it's not a vertical stress. It's a, like many mines here in Australia, it's a, we have very significant horizontal stress. So this is a stress condition for this mine. And we observed in these conditions, this many mechanisms have not far from closing crack model, and p-axis is subhorizontal. It corresponds to the maximum in situ principal stress. This is example from another mine. Again, this coloring of the tunnels indicates the maximum tangential stress. So we have a cluster of events here. In another view, they are located very close to the tunnel. Have p-axis orthogonal to the tunnel direction, and Hudson source type loads again sitting in this area, bottom right corner. And this is another example. So this is quite complex network of tunnels, and we see in this case it's quite small seismic event, so moment magnitude is below 0, quite tiny. But again, they have a similar pattern that Hudson source type loads there, bottom right corner, and p-axis have a tendency to be oriented orthogonal to the direction of tunnels. So the question is how to interpret these events and what the relation of these events to the problem we discuss here, to the rockbursts. With my colleague Alex Rigby, we did a numerical modeling of dynamic failure around the tunnels. So imagine you have a configuration, so it's a vertical section through the tunnel, and we have different shapes of the tunnels, and we tested variable loading condition. In this case, tunnel was loaded in horizontal direction, maximum principal stress was horizontal. In this case, maximum principal stress was vertical. Here it was inclined. And here we just tested various shapes of the tunnels and the type of the rocks. So I'll show maybe just a couple of animations. So what is shown here, it's a tunnel, vertical section through the tunnel. This is a case 1 where we have a horizontal maximum principal stress. Blue shows the part of the rock which is elastic, and this colored in magenta and light blue, it's a damaged rock. So pre-existing stress, it's already produces damage in the floor of the tunnel. And what we do here, we very slowly load the tunnel, that assuming there is a some, for instance, nearby mining, it slowly change stresses around the tunnel. And here you will see suddenly we initiated failure on the perimeter of the tunnel. So there is a one instant of time, there was a nucleated failure in the roof of the tunnel, and this fracturing started to propagate. And this process is dynamic. So it's not a quasi-static failure, it's a very fast process. And as this process happens, as you can see, it radiates seismic waves. So we have one process of evolving of this damage zone around the excavation, and this process accompanied by the emanation of seismic waves in the surrounding rock mass. So it happens fraction of a second, and in the end we have a evolved damage zone in the roof of the tunnel and in the floor of the tunnel. Another example, so now different loading conditions. So now stress fracturing happened in this, started in this corner, developed in the bottom left corner, and also this process happened in dynamic form, and it's accompanied by the radiation of seismic waves. And last case, it's a bit different. In this case, it's similar to case 3, but now we loaded this tunnel not by quasi-static stress, we loaded by the seismic wave. So we assume that there is some, for instance, blast or some another seismic events which send stress pulse, and as this pulse coming through the tunnel, it's initiate fracturing, which is unstable, and it evolves around the tunnel. So all this modeling, as we see that the fracturing around tunnel happened in dynamic form, it radiates seismic waves. The question is what the radiation pattern, what's the seismic source mechanism for this? And what we found is that we calculated seismic source mechanism of this radiation which was modeled, and all of them were in this bottom right corner of the Hudson source type plot near the closing crack model. So, and we call this kind of events, we call it crash type events, following the suggestion of quite famous paper of Ryder. So all mechanism which happened in this area, which are closer to the closing crack model compared to double couple model, we call it crash type events. So in all these model cases, we got crash type seismic source mechanisms. And we got seismic source mechanism. Obviously, we also got magnitudes of seismic events. So these are indication. These seismic events are not big. If you consider this failure happened along the section of the tunnel of 5 meters, so we'll get a magnitudes order between the 0 and 1. So it's relatively minor seismic events. And what we also suggested, because we cannot really interpret seismic waveforms or mechanism of these events in terms of the classical model of double couple model, or we cannot evaluate the source size using the Brune equation. We cannot evaluate slip velocity because mechanics of the process is different. So we suggest the expression for seismic moment tensor, which depends on the parameters of the stress and geometrical conditions, get geometrical configuration. So we're showing that it's possible to approximate tunnel and the damage zone by ellipsoid. And when fracturing, dynamic fracturing happened, we are getting another ellipsoid of a larger size. And a difference in dimensions of these ellipsoids, which equivalent to the increment in the depth of damage. These parameters control the moment tensor. And from this moment tensor, we can take a scalar moment, and scalar moment, we got this expression. Scalar moment can be expressed in terms of this combination of Poisson ratio, magnitude of maximum stress, And L3, it's dimensions of this fracturing process along the tunnel. So if it's happened over 10 meters or if it's happened over 50 meters of tunnel, so this must be plugged in this term of the expression. LA, it's a geometrical parameter, which we generally know. It's a size of tunnel plus pre-existing damage zone, LA. And finally, most interesting parameter was we can, from seismic moment, we see it depends on the increment in the depth of failure, DFA. So this is the most interesting part of this expression for seismic moment. And so we are arriving to another seismic source mechanism, which is useful in mines. So if we observe seismic events with significant implosive component and CLVD deviatory component, these events may be interpreted in terms of sudden stress fracturing around excavations. And previously I was talking only about tunnels, but excavation can be, it must be big excavation, it can be stope, it can be cave. So it's any type of excavation, sudden stress fracturing around excavation. And if we evaluate mechanism with a wavelength much larger than the excavation, so we will get this kind of mechanism. So we call it crash type mechanism when we have this composition of the isotropic and deviatoric part. So in Hudson source type plot, this mechanism will be sitting in this area. So this is how we, about specifics of seismic data recorded in mines. So we are, from one perspective, we are dealing with slip type seismic source events, and another type of events we are dealing with, we call crash type seismic source events. And this is very important to separate between these two type events because they define what the mechanics of loading of tunnels and what's the potential mechanism of damage. Because if we are dealing with slip type events, larger portion of radiation related to slip along the surface, then largest impact to the nearby tunnels will be in terms of shaking, and we are dealing with rockfall due to seismic shaking. But if the stress fracturing happened around tunnel in dynamic form, then we are talking about we will have crash type seismic source mechanism, and it will indicate that we should observe stress fracturing around tunnels, which may cause damage or may not, depending on intensity of this process and installed ground support. And this separation between source type brings us useful perspective to the definition of rockburst. Rockburst, as we said, rockburst, it's damage to an excavation that occurs in a sudden and violent manner and associated with a seismic event. So it's important to keep in mind there are two types of association. When we're talking about shakedown, it's a seismic event which causes damage. But if you're talking about strainburst, so we have a different situation when actually seismic events, it's a byproduct of damage. So the seismic waves don't cause damage, they are just radiated during the fracturing around excavation. And it's for problem of rockburst hazard assessment, it's quite important because there is a quite significant difference in the intensity of the loading of ground support in these two mechanisms. So here, these slides from this animation I showed earlier shows that if you are looking at the stress fracturing around tunnel and we measure peak ground velocity in the surrounding rock mass, so we are dealing with, in this case, values of up to 0.25 meters per second. So this is the intensity of ground motion in surrounding rock mass. And 0.25 meter per second, it's not very large ground motion. It's very hardly can damage ground support. And it's important, this radiation, it's not what caused damage, it's a rather byproduct of process. But if you look at what happened in this volume of fractured rock, here we are dealing with quite different velocities. And so this is another simulation which was done by my colleague Alex Rigby. So when he modeled the velocity of motion in the fractured rock, in the surrounding rock mass, as you can see, when this dynamic process of fracturing happens, 20 milliseconds, we see that the velocity of motion inside this volume, which is fracturing, is order of 2.5 meters per second. In the surrounding rock mass, velocity of ground motion associated with stress waves, seismic waves, it's much lower. It's all colored in blue. So it's a 0.5 and less meters per second. So in this case, it's not peak ground velocity of seismic wave which characterize the damage demand. It's rather this velocity which happened inside this volume. We call it a bulking velocity, which required to quantify the demand imposed on ground support. So in the end of this section, so what is important to take to the next step, I try to show that in mines we have two types of seismic source mechanisms. And if we're dealing with a slip type mechanism, it's relevant to talk about dynamic loading in terms of shaking, PGV. If we have a crash type events associated with the tunnels, then it's rather more appropriate to talk about dynamic loading in terms of bulking of stress fracturing ground. So this is strainbursting mechanism. And in this case, it makes more sense to evaluate bulking velocity. How much actually this fracturing happened? Is it happened over half a meter, 1 meter, 2 meter? What's the bulking factor of rock in this volume due to fracturing? And second and lastly, how fast it happened. If it happens 10 milliseconds or it happened 50 milliseconds, because these all three parameters give us a velocity of strain bursting or velocity of bulking. And what is important, PGV is not the same as velocity of strain bursting. If you want to quantify rock burst hazard, we need to evaluate these velocities separately because they characterize different mechanics of loading of ground support. Okay, so basically, last part of my presentation, how we use seismic data for this assessment. One block, it's related to assessment of ground motion hazard. And this is very similar to classical probabilistic seismic hazard analysis, which is done in the earthquake engineering. There is a bit of specifics of the mine, and the specific is related to we need to not only use recorded seismic data in the past, we need to try to forecast what a seismicity may happen in future. So this is example from a real mine. So this is a seismicity recorded during several years of mining, and gray it shows that historical mining, which part of the rock mass was mined out. And if, for instance, mine planning to mine deeper and extend stoping in a shallow part of the mine, the question is, can we use a seismic data recorded in the past as a proxy for future seismic response? And if you're talking about size distribution of events, for instance, recurrence times of large events or maximum size of events, then potentially, yes, we can definitely utilize this recorded seismic data. But if our question is related to spatial distribution of events in future, then historical seismicity may not be a good proxy for it, because as we expect this, mining goes in the deeper part of the mine, we expect more in future, probably more seismicity will be recorded in this area. So this is a difference with crustal seismology when we use typically historical seismic data and assumes that the future will be the same as the past, because geological processes, it's very slowly changing. In mines, we may not use this assumption. So if you talk about hazard in future mining, we need to model what the seismicity may be recorded may happen in future. So for hazard assessment, ground motion hazard assessment, we use both observed data and modeled expected seismicity for future mining. And after that, we utilize conventional probabilistic seismic hazard analysis, which includes 3 big blocks: seismic source characterization, characterization of ground motion, and these 2 blocks are combined into the assessment of it's a hazard curves assessment of NO rate of exceedance of given level of ground motion. So just bringing, say, mining specifics here. So our seismic source characterization, it's observed and modeled seismicity. Then we use size distribution to evaluate the recurrence time and expected next largest events. Ground motion, we need to calibrate ground motion prediction equation for the mine, and then we combine these 2 into and get a hazard curves and no rate of exceedance of different levels of peak ground velocity. So I may need to accelerate a little bit with my presentation, so I will skip details of the calculation of ground motion hazard, how we do it, but it's the key point. It's very similar to what is done in earthquake engineering in terms of probabilistic seismic hazard analysis. So this is example for the mine I mentioned before. So these are different locations of interest, and we can evaluate what's the peak ground velocity and no rate of exceedance and plot it on the in terms of likelihoods of risk assessment matrix established at the mine. So in this hazard, ground motion hazard definitely evolves. It depends which time period we look. If you look at November 2022, these hazard curves look like this. But for instance, November 25, November 28, this hazard expected to change because mining in future will change the expected future seismicity. So this ground motion assessment can be presented in terms of hazard curves, or also we can select particular probability and no rate of exceedance or likelihood and make a maps of PGV for corresponding probabilities. And these maps also evolve over time: November 2022, 25, November 28. So this block in rock-based hazard assessment, it's one way of utilization seismic data, observed data, model data. We can evaluate ground motion hazard, and it gives us what the extra dynamic loading of the tunnels, which contributes to evaluation of the extreme depths of failure. And also another contribution to ground motion hazard, it gives us extra kinetic energy. So when this fractured rock around tunnels, how this rock will, how much kinetic energy it will gain because of this strong ground motion associated with expected seismicity. So this is the first utility of seismic data. But there is another utility, and this is related to this model of seismic source, which I described above. If we select some seismic events which are associated with the tunnels and have crash type mechanism, then from these seismic events, we can evaluate using the seismic moment, we can evaluate depths of failure. Generally, we have good understanding what's the Poisson ratio, what's the loading condition of the tunnels, what's the geometrical characteristic of the tunnels, and then we don't know what is the L3 extent of the damage around the tunnel and what's the depth of failure. And assuming shape factor of distribution of damage or fracturing around the tunnel, we can invert this parameter from seismic moment. So, and we can do it for multiple seismic events which are associated with tunnels. And also another thing, it's important for rock-based hazard assessment to tell how fast fracturing happened around the tunnel, how fast the rock bulking and move into the excavation during the stress fracturing process, during the strain bursting. And here we can use again seismic data. If we identify events with crash type mechanisms associated with tunnels, we can evaluate so-called half duration of the source. So this was done by Dzivonsky Woodhouse 1983 when they worked with Harvard centroid moment tensor solutions. Technically, it's a time difference between the time source, origin time, calculated from the first arrivals of waves, which indicates the initiation of failure, and centroid time, which is evaluated from the moment tensor inversion and characterize the central time of the entire duration of the deformation in the source. So this difference between the centroid time and origin from first P&S arrivals give us the half duration of the source, and double of this half duration, this gives us the duration of the bulking process. It's, again, I emphasize, this is done not for all events. We need to select peak events which have a crash type mechanism and which are associated with the tunnels. Then we can evaluate bulking duration. And this is an example how it's done for different mines. Or if we have these events, this crash type mechanism associated with tunnels, for each event we evaluate strain burst depths from seismic moment and bulking duration from the method of Dzivonsky Woodhouse. And we got the values of duration, bulking duration between the 20, 30 milliseconds for the strain burst depths of the order of 1 meter, which is important for design of ground support. Another mine, this cluster of events close to tunnels. Again, for each event, we have a dependence between the strain burst depths and bulking duration. Again, this range of values between 10 milliseconds, 20 milliseconds, 30 milliseconds. And this is another example, crash type events associated with tunnels. Very small events give us very small depths of fracturing, 10 centimeters, and duration also 20, 30 milliseconds. And this is a data from different mines which were published. So we have quite good and general consistency. At some mines we have a faster fracturing, which give us larger kinetic energy in the demand. Some mines it's a bit slower, which give us a lower kinetic energy. So this bulking duration assessment, it allows us to evaluate bulking velocity, which gives us another way to assess kinetic energy. It's in parallel with a PGV, which we get from ground motion hazard. And finally, there is another utility of seismic data. If we have a multiple crash type events associated with tunnels, and if we go back to this example from the mine, for instance, if you look at this tunnel and we recorded one crash type event around this tunnel, another crash type event, each crash type event is interpreted as a deepening of the depth of failure. So we can say that actually in this part of the tunnel, there is each event represents the episodes of growth of the damage zone. And we can invert amount of this depth of failure for each event, and we can accumulate it. So we can say that around this part of the tunnel, fracturing happened. As fracturing happened, rock mass bulks, it extends the rock bolts. So it consumes capacity of these rock bolts. And for instance, this part of tunnel, we don't observe seismic events. We may not say that probably this consumption of ground support capacity doesn't happen here. So this is application of seismic data. We can take multiple crash type events associated with the tunnel, and we can transform results to all of them collectively. What's the deepening of the depth of failure from all of these events? And yeah, this is example from one mine, another mine. And this mine we get very large values, and this is where really this mine there was quite massive damage in the excavations. And this mine, this increase of the depth of failure is very small because these events are small and we have very small values. It's less than 0.12 meter. So if we evaluate this cumulative depth of strain bursting, it goes and give us the information how much displacement capacity of ground support consumed. So it's another contribution to our assessment of demand, capacity, rockburst hazard. So as this part of the presentation, I'll try to show that in months, if you take observed model seismicity, we can evaluate using the conventional probabilistic seismic hazard analysis ground motion hazard, and this gives us the quantifies demands for shakedown damage, and plus it gives us the extra dynamic increment of the depth of failure, extra component for strain burst damage. But this is not only way how we evaluate rockburst hazard. It's also important to evaluate another contribution from another damage process, sudden stress fracturing. And for this type of demand, we utilize crash type seismic events, which are associated with the tunnels, because these events help us to parameterize the demand in terms of duration of bulking, TB, and also it can help to assess how much capacity of ground support consumed over time. That's all. Thank you for your attention. So there are some publications on this topic which are available, or I can provide it if they're not available. Thank you for your attention. Any questions?
Thank you very much, Dima. Thank you.